What?
Yeah, so where will you find? Is there any library in?
I think online is your best place for resources here. What's wrong?
I gave him an idea.
A good idea.
Okay, great. Great, alright. We'll have a look at the next lesson for mechanics then, okay? And this lesson is important for one of your experiments as well. Okay.
Last lesson?
On mechanics, yeah. Okay, so this last lesson, if you want, oh sorry, I need to open the slides of course. There's not a lot to do in this last lesson. It's actually just some theory to go through. Everybody's hungry. I don't know. So have mercy on me, please. Okay. The pendulum. Right, there you go. Yes. You're always yawning in my class. Do you yawn in the other classes too, or is it just mine? For example, would you yawn like that in Lorraine's class?
You never.
Would you? Would you?
He would.
No, you would you?
No, I don't.
You would not.
He does.
Does he? Okay.
It's just a normal thing.
Not if you knew what's good for you, you wouldn't. Okay. The pendulum. Lorraine wouldn't like you sitting up the front for a class yawning, I promise you.
Even if we are like, we sit in a group.
No.
It's not
no,
good.
Don't do it. Alright, the pendulum. Okay, you got this?
Yeah.
Pendulum, yeah. Okay. Some of you know what a pendulum is already. Fulong, do you know a pendulum? Show her a pendulum.
String and a ball.
Yeah.
Yes.
Moving.
Like this.
Extreme.
Beautiful. There. Like this, yeah. This is a pendulum. Yeah. So here is some terms for the pendulum. So you have equilibrium is in the middle. You have a massive bob and massless rod, amplitude, and so on.
What's massive bob and what's bob?
Yeah, bob, not the person Bob. Bob is a little ball. So a massive bob means a very heavy.
So this is a bob.
Huh?
Mm-hmm.
A ball. Yeah.
But
bob is actually more of the term you would use in an experiment for. You wouldn't say a ball. You'd say bob in an experiment. Or you could say a lead weight. You know lead, this material?
Yes, PB lead.
PB, yeah. Okay, can you draw this, please?
Okay.
This one is a good experiment.
It is a good experiment.
We'll take the time.
Yep, we'll do this one, yep. Yeah. Okay, it shouldn't take you too long to draw that. What time is that Halloween party at? 2 o'clock?
3.
3 o'clock. Okay, got that drawn? Right. So let's have a look at this in more detail. Okay, I'm going to draw it here. So we'll say the pendulum has a length here of L, and let me just draw in some lines. So this is going to swing down here, and then it will swing over to here, correct? Yep. So I'm looking at this motion here as it moves left and right. What is this motion called? Simple harmonic motion. Now, it's not really simple harmonic motion, because simple harmonic motion is like this. But it's not really doing that. It's actually kind of going down a little bit. So we say it's roughly simple harmonic motion. The reason it's not exactly is because we want it to go like this, but instead it dips down a little bit.
You mean that it swings?
It swings, yeah, rather than slides.
Oh,
But it's nearly simple harmonic motion, and that's good enough. So we'll call this here theta. Yeah, we'll have to start using theta. You're okay with my theta? Yeah. And this one here, we'll call it S then. Now, there are two forces on the bob. What are the two forces here?
wait.
Very good, the weight. And what else?
Up.
Yeah, what's this called?
The arm?
This one.
Yeah.
Tension. Tension. Yeah. Okay, now, let's just zoom in on this for a moment. So here we have our T. So I want to make it this direction. Yeah? And this direction. So if this is theta, now don't just say it. Think before you say it. If this one here is theta, top or bottom, which one here is theta? Now, I don't say anything for at least 5 seconds, so I know you've thought about it.
Where is the theta?
Here. This is the first theta. I want to know which one here is theta. Top or bottom?
Bottom.
Up, down, down.
Top,
Top.
because
Of the X.
Yes.
it's it's the one in the Z shape. If this is theta, then this is theta. So it's the top, again, please.
Like it's not opposite, yes?
No, it is opposite. This one is not theta,
Yeah.
it's this one that's theta.
Oh,
So, is this cos or sine?
cos.
Yeah, T cos theta, and this is T sine theta, and this one here,
Sine.
mg. Now, is the bob moving up and down? Kind of, isn't it? It's because it's going up and down a little bit.
It's swinging up and
Yeah, but only a little bit.
Yeah.
So we will say roughly it's not.
Okay.
So we will say roughly T cos theta is roughly mg. This is our first equation. Okay. Now, what about... so we have this here, T cos theta is mg. Now, let's see what else we can make. If this is L and this is S, how much is this side?
Square root of L squared plus S.
Yeah. But remember we said it's not really moving up and down, like it is a little bit. So here to here is about the same as here to down here. I know it's not. I know it's actually a little bit shorter. So remember, we're just doing this roughly. Here to here is L.
Okay.
Again, because it's just swinging down. Is here to here L? No, it's actually a little bit shorter. A little bit. But we'll say it's roughly L. And that's okay for what I'm doing today. So what does cos theta roughly equal?
L over S.
No, try again.
Opposite of
L
Over S.
over, no, over hypotenuse in this triangle, if this is the right angle.
Over E.
L over L.
Yes.
So it's actually roughly equal to 1.
Okay.
So then we get this result, that T is roughly equal mg. Not exactly, but nearly mg.
Opposite over.
No, adjacent over hypotenuse is cos.
Yes. Okay.
Right, so what I do now is I take this and put it in here.
So it will be sine.
So this force going to the left, that will be T, which is mg, sine theta. Okay, now can everybody look up here, please? What is sine theta roughly equal to? But sine theta is roughly what over what?
Hypotenuse S
Over
L.
L. Roughly. So I can use that result here and I get F is roughly mgs over L. Or if you want, F is roughly mg over L S. And I suppose because it's going to the left, I should put in here minus. Yeah.
Now it's F equal mg sine theta.
Yeah, here it is here. Is this what you mean? Oh, sorry. Oh, yeah. T sine theta, yeah? But what did I say T is?
Roughly mg.
Roughly mg. So, mg sine theta. Okay. Newton tells us what's F. What's the formula for F? So now we have ma is roughly equal to minus mg over ls. What happens here? Cancel the m. So we get a equals minus g over ls. Now, what type of acceleration is this horizontally? No, what I mean is it circular? Simple harmonic? What type is this one? Simple harmonic. So we can use our formulas for simple harmonic motion because we said simple harmonic motion. So what is the formula for acceleration? But A equals minus omega squared s. No, it's like this. It's like this, yeah. So if I make these equal now, if I call this 1 and 2, if I make them equal, I get minus g over ls equals minus omega squared s. What happens here? Cancel the s's, cancel the minus. So then that means we get omega squared equals g over l. So what does omega equal? Square root of g over l. What's the formula for time?
Time.
2 pi over omega.
No.
Therefore, the time is equal to 2 pi root L over G. This is the formula to work out the time for the pendulum to swing once. You might have seen this formula before. One and back, yeah.
Is the proof in the
This is proving it, yeah. No, but it's in your lab report. Yes, how far? This much? Here's okay? Have you seen this proof before?
This proof, but this formula
Yeah.
and the experiment.
Yeah. But it's good to know where the formulas come from. They don't just fall out of the sky, you know. Now remember, this formula is not accurate, but in fact, when you actually use it, you find that it's really, really accurate. So, I know it should be like this, but actually, it's pretty good. The only thing is, the theta should be small. As long as the angle is small, the time formula, it works pretty well.
Because it's not.
Yeah, because the up-down motion is not so exaggerated, yeah. And in fact, the smaller the angle, the less up-down there is, and the more simple harmonic motion it is. Okay.
And the smaller
There's less vertical motion, yeah. If you pull the angle really big, this is not simple harmonic motion. This is simple harmonic motion.
like the one in the amusement park, there is one.
Yeah, that's definitely not going to work for that.
Yeah, but
Yeah.
it has.
It might work maybe like a child on a swing, but still, even that I don't think would be
Yeah,
great.
But there's
A clock. Clock
Mm.
pendulum.
Like this, like
No, clock pendulum.
With the bell.
Grandfather clock.
Yeah.
Yeah. Old clock, yeah. Okay, can we scroll down? Yeah. You got this? Yeah. So, I want you to try, use the formula to get the answer here. How long would it take a 1 meter pendulum to swing, now wait, swing 10 times? 10 times. Try this one.
One there.
Hmm?
You want there?
The L I give you, it's 1 meter. I want to know the time. Oh yeah, sorry, yeah, I keep forgetting this. In English, we use how long to mean the length and also the time. So if I said, how long is class? You don't say class is 10 meters long, even though maybe it is 10 meters long. The answer is 50 minutes. Yeah. So in English, how long is both this and time? Did you know that already though, or? Not everybody, because sometimes in the exam this confuses students. So here, how much time would it take? Okay, try this.
T equals 2 pi L over
2 pi root L over G.
the one multiplied by 10.
Yeah.
People have to do.
You have an answer, Adnan?
20.
That sounds about right, because 1 should be about 2 seconds, so 10 of them would be 20 seconds. Yeah. So let's have a look. The time is 2 pi root L over G, which is 2 pi root 1 over 9.81, which is, what's that, roughly 2 seconds. Yeah, so it takes 2 seconds to go like this. So 10 times? 20 seconds. Pretty easy, once you see it, yeah? So what we'll do is, we'll do the homework together. It's not that difficult. So we'll just take turns of doing the questions together, and then that's the mechanics finished. Okay. There's only one question.
Only
Only one question, yeah. Just one question.
So legit.
Totally